Today I am going to define spin orbit coupling, LS coupling and JJ coupling. Before starting my lecture, we will differentiate between notation. If we are talking about angular or azimuthal quantum number, then we will use L, S or J, where L is orbital quantum number and S is spin quantum number and J is total quantum number. Now move on angular momentum. When we are talking about angular momentum, then we will use capital L and capital S and capital J. Capital L means orbital angular momentum, capital S means spin angular momentum, and J means total or resultant angular momentum. So what is spin orbit interaction, or we can say that spin orbit coupling? When we are talking about one electron, then spin orbit coupling comes into account, because we know that electron do orbital motion in their shell and also it do spin motion around its own axis. When any charged particle comes in magnetic field having magnetic momentum us, then an interaction energy create among them is equals to minus mu s dot b. So what I have written here, interaction energy between magnetic field b due to orbital motion of electron and magnetic momentum us due to spinning motion mu s, known spin orbit interaction, and this interaction energy is equals to minus mu s dot b. So what is happening here? Due to orbital motion, a magnetic field is created here, and due to its spin motion, a magnetic moment created here. Then these both are interacting here, orbital motion and spin motion. That's why we call it spin orbit interaction. One more thing I want to clear before starting my lecture. If we have two electron A and B having angular quantum number L1 and L2, then if we want to find a resultant, then you cannot do L1 plus L2 simply, because we know that angular momentum and angular quantum momentum is vector quantity, so it will follow vector sum of quantum mechanics. So resultant angular moment quantum number is equals to modulus of L1 plus L2 to L1 minus L2. This is very important thing, and this will follow for spin quantum number and resultant J quantum number also. Now move on angular momentum. Now if we are talking about orbital angular momentum, then it is denoted by capital L. So its value is equals to under root L plus 1 h bar, where L is angular quantum number and L is angular momentum. Now if we are talking about spin angular momentum, then it is written as capital S, and it depend on spin quantum number under root S plus 1 h bar. Now if we are talking about resultant angular momentum, then its value is equals to J plus 1 h bar, where J is L plus S to L minus S. Now we are talking about LS coupling. So why we call it L and S coupling? For two or more than two electron, LS coupling works. As you can see that spin orbit coupling works when we are talking about one electron, and LS coupling works when we are talking about two or more than two electron. Let's take example. Let we have two electron A and B having azimuthal quantum number L1 and L2 respectively, and spin quantum number S1 and S2 respectively. Then L1 of A and L2 of B interact in such a way that they make a resultant L, which value vary from L1 plus L2 to L1 minus L2. And then S1 of A and S2 of B interact in such a way that they made a resultant S, whose value will vary from S1 plus S2 to S1 minus S2. Then this resultant L make a resultant angular momentum, and this S make a resultant spin angular momentum. Then they both coupled it's L coupled with resultant S. That's why we call it L-S coupling. Because we know that L equals to under root L plus 1 H bar, this L is resultant L. And S equals to SS plus 1 H bar, this S is resultant S. Now put these two values here. Then resultant angular momentum is equals to H bar LL plus 1 plus SS plus 1. So what is happening here? Their resultant L coupled with their resultant S. That's why we call it LS coupling. And one more thing, it works for low value of Z, where spin orbit coupling very low compared to LS coupling. Now what is JJ coupling? Because we know that resultant angular momentum we denote by J. So when resultant angular momentum coupled with each other, then we call it JJ coupling. It acts for higher value of Z. Let's take example. Let we have two electron A and B. A have azimuthal quantum number L1 and spin quantum number S1, and B has azimuthal quantum number L2 and spin quantum number S2. Then resultant of A when coupled with resultant of B, then we say that it is JJ coupling. As I have told you that orbital angular momentum and orbital quantum number always follow vector addition. So J1 will vary from S1 plus L1 to S1 minus L1, and resultant of B electron is equals to S2 plus L2 to S2 minus L2. So when resultant of A will interact with resultant of B, then we known as JJ coupling. Then again this J1 and J2 follow vector addition. So resultant J will vary from J1 plus J2 to J1 minus J2. It is very interesting. And the resultant angular momentum is equals to J1 plus J2 plus J3, so on. Take an example. Let we have two electron A and B. A has spin quantum number S1 equals to half and azimuthal quantum number 1, and B has half and 1. When we want to find the resultant of A equals to J1, then it will vary from 1 by 2 plus 1 to 1 by 2 minus 1. So it is equals to 3 by 2 and 1 by 2. When we want to find the resultant of B, then it will vary from 1 by 2 plus 1 to 1 by 2 minus 1. Then it is equals to 3 by 2, 1 by 2. Then we want to find coupling between them, J1 and J2. Then it will follow again vector sum rule. Then it is equals to, take first two combination 3 by 2 and 3 by 2. Then it will vary from 3 by 2 plus 3 by 2 to 3 by 2 minus 3 by 2. That is equals to 3, 2, 1 and 0. So what we have seen that when spin of an electron interact with orbital motion of this electron, then this is known as spin orbit coupling. And when we take two electron into account, then resultant L of these two electron interact with resultant S of these two electron, then it is known as LS coupling. So what is JJ coupling? When resultant J of first electron and resultant J of second electron interact and make resultant J, then this is known as JJ coupling.